Okay, welcome everyone. So welcome to Cloud Computing and Big Data today. And today is a very nice lecture about Lecture 11, Big Data Analytics and Cloud Data Mining. And we have an invited speaker who is Ph.D. student Chadi Barakat. So could you introduce yourself perhaps a little bit?
Hi everyone, I'm Chadi Barakat and I'm one of the PhD students working with Morris right now. I'm doing my PhD in bioengineering and my main project is in the medical field, but I'm also working on several projects in parallel with Morris and Rocco and Gabriele, who you've already heard from in the last few lectures. And I'm excited to actually do this. So let's see how it goes.
Right, and he will talk really as an insider from using big data analytics basically daily on our cloud machines, using data mining techniques like a priori, FP growth, algorithms that stand the test of time, sometimes a bit simple, but still also simple jobs and simple algorithms are sometimes really the way to go. There's even a machine learning principle called Occam's razor saying simple model better. And Shadi will basically explore with you this topic. We started with this a little bit actually before we really started the course with this pre-lecture on Jupyter notebooks. If you remember, I finished a little bit with the outlook that we will learn more about association rule mining. So going a little bit into shopping data and so forth. Then on another interesting aspect, we have seen deep learning a lot. And this was usually user-facing. We wanted to have a classification in remote sensing, what type of field it is. Is it water? Is it grass? Or things like a car or something like this from out of an image. But deep learning can be also used to mine data, which is here shown today, basically also by Shadi later, which is interesting, thinking about that this is then not really user-facing anymore, this deep learning. It's just helping essentially to have a better database that then is, of course, queried by users. But before we go into the material of this, as usual, let us review what we had the last time. Shadi, if you go one slide ahead, thank you. So the last time was really then essentially the top of the mountain when you think about all the different cloud stacks we have been running through, right? We started in lecture 8 with infrastructure as a service, which was the lowest level in a sense, really talking about hardware resources, storage, thinking about computing, but also, of course, networking. You have also explored in the assignments, security keys, of course, also play along with this, that are once somehow locked down in the hardware. When I switch a region, usually the security has to be readjusted, new keys have to be created. Then the one that is on top of this, we kind of said it's PAAS. So here we're talking about much more, let's say, platform as a service, that you have essentially virtualized different environments which are oriented more towards developers or essentially people that develop, again, something in the cloud on top of this platform. And then on the highest area, which we had the last time, was then really software as a service, which in the end for a user is nothing else than swiping the credit card for some particular service. Now we learned that some services are free. So Google Docs, you know that, or Google Maps are good examples of brilliant SSA, software as a services, of course. But of course, take away the message that they make their business model differently, right? It's not based on a credit card, but it's based on ads. And ads we will look into together when we review AdWords and AdSense, which is a complementary part to it, basically in lecture 14 when we talk about it. Other regions where we have seen a remarkable business is possible in CRM online. So customer relationship management is really a very broad area, which we have seen also in different examples from Fresh Sales, but also from Zoho. They do a lot of cross-selling as well. So once you have a CRM, then of course the enterprise resource planning is also just one step to the right. One step to the left is maybe Zoho Mails. and other business sectors that you can come into very easily because you're once already inside the SaaS systems. And of course, there were lots of benefits. If you remember, you don't have to worry anymore about updates, rollout of software that much as you had done in times where we, went downtown and get a physical copy of the software. Today, by having everything online, by being ready essentially as a software ready to run, right? You don't have to even install usually. You just go to the website, log in. Of course, we have seen there are either subscription models or you swipe your credit card for some other thing in terms of time credits or whatever it is. This is a business model behind it. And of course, it works particularly well, especially because you have this horizontal scalability that you see also on the right-hand side. No matter how many people log into your website, essentially, when you follow this paradigms of the cloud with this idea of virtualization that we picked up from lecture 4, then you can very quickly expand and scale really to many users. And of course, this is quite attractive, and you don't really have to do much for it. You have seen, or you will see also in several of the upcoming lectures when we talk about containers. Kubernetes is a container orchestration service that automate a lot of these processes of deploying essentially your application in the cloud, and we will talk about it. A final statement when you think about why that affects us here also partly in terms of parallel and scalable machine learning, you could also see that no matter where you go in which cloud you are, whether it's Amazon, you have the Amazon SageMaker, which was really an integrated development environment for machine learning, a really nice software as a service model of creating beautiful machine learning models. And of course, the other way, if you want to think about some user application in terms of customer relationship management, again, we have seen Freshsales. There's an AI plugin that you can, of course, buy and subscribe to, or depending on what subscription mechanism you use, you get this module, of course, inside your subscription mechanism. And with this, you have lots of recommendations, which are for a company that really relies on products, on customers and sales, can make a huge difference of having, let's say, integrated, personalized recommendations of what this person will going to buy. And if you essentially go and call this person, what the customer relationship management also tracks in terms of calls, in terms of emails, the Facebook profile, which can be easily accessed. So there are lots of different aspects which we have introduced. And I think that's all I really wanted to leave on the table for you. Just think about two things when I'm finished here with SaaS. Every time your data is somewhere, and think about the security, right, when you are in these systems. And yeah, the second is really just explore it. I think it's the future with SaaS. So we will see almost none, and we see it in gaming everywhere, in really production software like Microsoft Office for really work. Everywhere you go, it's going online. Right, and with this, I think I'm done. Chadi, take it from here.
Okay, thanks for the brief introduction, Morris. So yeah, this is lecture 11 of the course, and we'll be mostly talking about big data analytics and cloud data mining. Mostly, I'll be trying to infuse some of the experience I've had in the field into what we're talking about, but I'll try to bring it all back together in the end, in the conclusion of this course. Hopefully, it'll make a lot of sense by the end, but it's going to sound a bit dissociated at the beginning, so bear with me. All right, so first of all, we're going to talk about association rule mining in big data, and mostly defining it, but this is something that's already been done in the beginning of the course. And then I'm going to define one of the projects that we're working on, which deals heavily with retail and commercial applications. And to do that, we're going to talk also about some of the algorithm that we implement in our work there. And it's like these two algorithms are the ones that are most commonly used in association rule mining. And when you use these kind of algorithms with as big data as we have, you have to face a few challenges, and then we have to go through how we overcome these. And finally, we'll go through some slides about how this applies in the cloud. And this is going to be part 1 of our lecture. And we'll take a short break, and then we'll go through how we use deep learning as a data mining application. And this is mostly a refresher about everything what is deep learning. And then also another application that we're implementing with Onforoff. And yeah, let's go through with it. So first of all, let's talk about association rule mining. Mostly it's just another way of finding connections between what people buy. So it's mostly, we as humans, we look at one thing and then we see a result and we associate this. Thing A happens and then thing B happens, so A and B are related. But it's always for us a one-to-one relationship. But algorithms mostly that implement some kind of association rule mining, they're able to detect things on a broader spectrum. They find some relationships that we as humans cannot find. And this is very, very lucrative in terms of like commercial applications. So you see this a lot on your Amazon shopping, or when you're buying stuff online. You see it, like people who buy this product usually also buy this product. And it's usually always spot on. And that's based mostly on a lot of research that's done in the background that you're not aware of, but it works. And there's also a lot of money being paid into improving these algorithms. So mostly it's done by creating rules. And these rules are based on the frequency of some items that are bought together. So let's say object A and object B are always bought together, and then there's another object that's bought afterwards. So that creates a rule that when A and B are bought together, object C is probably a good recommendation for this kind of shopping basket. So the association rule mining algorithms, they identify these rules. They make it easy to find them in the long list of shopping baskets that a vendor might have. And they present them for some analysis. And this is a kind of unsupervised learning, unsupervised machine learning method, because mostly there's no input from the people. The only input that we're giving is data. We're not trying to train it. We're not trying to tell it if it's doing the job correctly or incorrectly. It just does it, and it gives results. And the two main algorithms that are used in industry right now are a priori and FP growth. But of course, there's a lot more than just that. But mostly these are the ones that were established at the beginning, and well, people don't like to change that much. So let's stick to a priori and FP growth for now. So mostly this is one of the main examples that's used in almost every introductory course to association rule mining, which is the shopping basket for bread, milk, and butter, or cola, or eggs, or diapers. So mostly it's just, it illustrates a rule based on a strong relationship between the sale of diapers and the sale of beer. Mostly because several baskets show that when people buy diapers, they also buy beer. And in the background, if you think about it, it's mostly the people who are usually buying diapers don't have the time to go to the bar and enjoy a beer with a friend. So mostly they buy it at the supermarket. So in this case, it would be interesting to create this kind of rule where recommend beer to people who buy diapers. So this investigation into the transactions and finding frequent item sets, it seems to be easy when you look at it like this in such a small data set. But as the data set gets bigger and bigger and bigger, it's not something you can do by hand. So you have to implement this kind of algorithm that does it. And the more transactions you have and the more objects you have in these transactions, the more complex it becomes. So it gets more interesting to automate the whole process. And that's how we get to where we are right now. And these rules try to help identify new opportunities for selling products that don't usually go together. I mean, you would understand that people who buy bread also buy milk and eggs, but why would you go directly in the direction of beer? So this is also something that encourages, in a way, it encourages the economy, and that's always good. So for our application of this whole process, we're working with as part of the Onforoff project, which is a German project. And it's mostly a project that tries to bring together the huge amount of data that's collected from day-to-day operations of industry partners. One of our customers sells a lot of perfume in here, but it also, like, it's these commercial platforms that sell online and also in physical stores. They sell everything, from, of course, perfume, but also lotions, shampoos, soap, beauty care products, all of these things. And they have this huge amount of data that's accumulated over years and years. But if they're not doing anything with it, this is just wasted data. And it might help them a lot to actually use this data to improve their sales, because mostly the main purpose of their work is to keep the customer. And if you keep the customer buying, then you're improving your sales, then you're improving, well, you're widening your pockets. So if you have a lot of data, this is a fertile ground, as they say, for creating association rules, for actually learning new things about the behavior of the customer, but also about which products sell, and which products sell better when they're merged with another product as a package. So when we're given all of this purchase data that's accumulated over years, and we build this market basket transactions, we have a way of improving the sales, but also improving the experience of the customer themselves. So we have this chance to do it. And so we, as part of the Onforoff project, we're trying to improve this by trying to learn what the customers are mostly interested in. And to do that, we apply some kind of association rule mining for mostly three purposes. The main one is to find associations in products, but also to find these associations, how they differ from one store to another, from one city to another, but also, in the end, to make them personalized so that every customer, when they log into that website or when they walk into that store and present their customer ID that they have from the store, they would get also personalized recommendations. In a way, that kind of makes the customer feel a bit more special, but also it improves the whole experience also for the store. So the main algorithm that we use initially is, well, everyone uses it, is mostly a priori. And it's quite simple on paper. You have a table of transactions. You go through it the first time, and then you make a list of every unique item that you have. And then you see for every item how many times it appears on the list. Initially, when the algorithm was created, it didn't have a kind of pruning process, but they realized that it might have a problem scaling up. So they reintroduced a pruning process where there's a minimum support that removes any product that doesn't have this kind of, let's say, 50% appearance. So if it appears in less than 50% of all the market transactions, then we can ignore this product as a non-common product. So this initial list of products, after you remove from them the infrequent items, is your list of frequent items. From this list of frequent items, you create another list, which is the list of 2 item sets, as you can see here. Well, I don't know if the pointer is visible, but you get this list of 2 item sets where every 2 products are grouped together from the frequent items, and you try to see how many times this pair of items appears in the transactions that you have. From this list, you also remove the non-frequent items, and then you run again through through your data set and try to see which 3 items, and so on and so forth. If you have a large enough list, you can go all the way up to, if you have a list of, let's say, k unique items, in the end, you might have a list that has k-1 item sets. So a list of items that, let's say, a list of frequent items that has k-1 items in it. And it can grow, but it depends on how many times these items appear together. And so it's a very good way of showing which items usually group together, and it works. Otherwise, it wouldn't still exist after so many years it was created. The only problem here is that you have to iterate over the whole list every time. So from between every step, you have to go through the whole list and repeat the whole process of pairing every item with another item, or every 2 items with another 3rd item, and et cetera, et cetera, et cetera. So that, you can see right now that that might pose a problem eventually, as your transactions list grows bigger and bigger, and your items also grow bigger. So let's see, mostly after like you learn the theory about this, we try to implement it like actually in the programming. We try to program it into the, sorry about that. So we try to implement the algorithm programmatically. And in Python, mostly that's the kind of software I'm working with. In Python, we have a library called MLExtend. And built into this library are a set of machine learning algorithms. One of them is a priori. Next, we're going to talk about FP growth, but for now, we're concerned with this one. And so you mostly have to just load your data as a list of products. Mostly it's a list of transactions. And then you binarize these transactions. That is, you make a list of all of your items, unique items, and you just tell where and which transactions these items appear together in. And usually this file can get quite big, because if you have, let's say, just 7 items and 15 transactions, you have an array of 7 by 15. But if you have, let's say, 40,000 items in a market basket, in a list of 28 million market baskets, then you have quite a big table. And some of these tables can grow up to like 165 gigabytes, just as encoded lists. This is not even looking at these associations. So regardless of this, you make this binarized list, and then you just simply run it in through the algorithm, which is 1 line of code. But again, if you guys already know or have done some programming before, you already know that 1 line of code might take half a second to finish, but it also might take maybe years to finish. It just depends on what kind of thing you're trying to implement. So this is the problem that mostly a priori runs into. While trying to create this list of frequent items, a priori is going to go through that list of binarized items as many times as it takes to find as many frequent item sets as it can, as long as these item sets fit the minimum support threshold that we set for it. So keep in mind how big this list might be if your list of transactions is also big. And from this list of frequent items, then we just apply a calculation process to find the association rules, which is the important part. But mostly if you're making these associations on unclear data, it produces results, but these results mean nothing. So mostly the important part from all of this is building a proper frequent item set. And this is what a priori is doing right now. So here we get to the problem with a priori. And I already talked about this, which is mostly scaling up becomes very problematic. Because if you have to go through the list over and over and over again, that's going to be very computationally expensive. So the solution to this is mostly, fine, you can grow your you can increase computation power, but at some point you're going to run out of it. The same goes for, like, if you reduce your data set, then you lose the accuracy of your algorithm. So in the end, what you have to do is prune, but that might not be effective in the end. It will only get you so far. So you probably have to find an alternative. And the main alternative in terms of association rule mining is FP growth. So FP growth kind of starts off in the same lines as a priori. It looks at the list and it runs through this the first time and tries to see how many times each item appears. But after this first pass, it doesn't go through this list repeatedly. It just goes through it one more time. And during that one more time, it starts building connections like this tree. And then this tree is called the FP tree, which is the frequent pattern tree. So instead of recursively scanning the transactions list, it goes through it will go through the first time, and then it starts building branches of these three, so that in the end you can clearly see which products are mostly associated one with the other. So in the bottom right corner, you can see that product A, B, and C are quite associated one with the other, because mostly they have this large number of support. Technically, how this tree is built is mostly that you start off with one product that has the most appearances, and then from it you try to build branches. So A and then B and then C, they're common, and then A, B, C, D, etc. And then it gets more complicated as you grow, but at the same time it's still quite visible which products would usually be associated one with the other. And in this, you don't have this computational complexity of running through a list hundreds, maybe thousands of times if you have 1,000 products. So it looks like something that seems to scale well. And in fact, it actually does. Even on the website for ML Extend, where they describe their code and they talk about it, they show specifically that ML Extend, that FP growth scales a lot better than a priori, even their implementation of a priori that uses less memory. It grows well with the data, and it doesn't, and it's not really affected by large amounts of data or large amounts of unique items in the data. So implementing it in terms of implementing it in Python, also it's easier, it's faster, and it's more streamlined. Now, of course, it's going to be a problem when your data grows so much. Going back to the example that I was using, in our case, we have a list of 2.8 million transactions with 44,000 unique items. Of course, FP growth is going to stutter with this. It's going to suffer quite well with this. But this is where your experience comes into play. This is where understanding how FP growth works and how you can make it work better comes into play. And at the same time, there is a lot of research that you can find about parallelizing FP growth and applying it on a large scale. So there's always a solution if you're willing to look hard enough for it. Some of these solutions also include using the cloud for this stuff, and this is going to be the subject of the next lecture that Morris will give. But mostly, when you don't have access to resources where you can run this kind of these kind of algorithms, you have to depend on cloud resources. And IBM Cloud Pak for Data is one of these resources, and it has several modules for association rule mining, and it's a fully integrated data and AI platform. Similarly, it enables you to run the OpenShift enables you to run IBM Cloud Pak for Data platform on clouds like IBM Cloud, Amazon Web Services. But there's also several other ways of implementing FP growth. For example, via Apache Spark on MS Azure. And the same, I would say, would be possible for Google Cloud Platform, or even for Amazon Web Services. So these services are available for you to use online when it's not possible for you to do it locally or via access to a supercomputing cluster. I don't think a lot of people have that or can say that. So it makes it more accessible for everyone to do this. And also it allows for research to be done more easily. And with that, I guess we're done with part 1. And I don't know, should we take
Thank
some
you very
questions?
much. And I'm not part of the recordings because of GDPR and so on. But it was excellent lecture. Thank you very much. Looking forward to the second part of it. I think just for putting it into context, the last couple of slides, of course, think about that the Jupyter Notebook, as you know by now, is not really parallel, right? It is there. It's a interface to something. And we learned now a lot of different clouds, which is, of course, goal of this course, right? That you touched basically on Amazon Web Services. You used MS Azure, you use Google Colab, you use different ones. And all in one form or another provide you opportunities to use also data mining techniques. And just think about that. Of course, it is important that the algorithms themselves are also parallel, because the ML extend library in itself is not. So Chadi did some work to distribute it around a cluster. In our case, you have seen essentially one step back, the slide that you have seen Apache Spark. And the Apache Spark has this interesting machine learning library, if you remember, that we had in lecture 3 and lecture 2 respectively. And this is a parallel implementation based on the parallel engine of, basically the Apache Spark framework. And with this underneath, your Jupyter Notebook then will scale based on this infrastructure. So that's important really to realize that a Jupyter Notebook alone is not enough. You always have to think about what's behind it. Also, if you think about the AMI image that we discussed, basically in the Amazon Web Services, when you run a Jupyter Notebook there, of course, now you have to think about that as just a virtualized environment, a kind of computing, and you have to fit the resources to it. So if you want to run something very large with lots of memory requirements, you have to pay the price and get a huge memory CPU for it. Or as you have seen in one of the assignments, essentially that convolutional networks just dies almost when you have a very, let's say, cheap CPU, right? Deep learning needs GPUs. No matter how nice a Jupyter Notebook is and everything works nice for, small examples like neural networks, which are, let's say, in the typical feed-forward artificial neural network sense, 2 hidden layers. In the end, it depends what infrastructure is behind the Jupyter Notebook. And I think by now you should realize this and also know the game here from the cloud data mining, where there's nothing else really. If you want to run FP growth in a very scalable way, you have to make sure that your infrastructure behind essentially your Python code is really scaling up, or have a different way of doing it. Of course, there's solutions like the IBM Cloud that was also presented that have also inherent ways of parallelizing it. Spark is very explicit, of course, it's open source, and so everybody knows how that works. And MLlib is essentially something you can just download and use if you have your Apache Spark cluster. So then you know how it parallelizes. Right, but this I think is all I wanted just to contribute to this last couple of lecture slides here, and I think we break now for 10 minutes and come back to the second part of the lecture that will be given then by Chadi as well.